Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are in the Big Ideas Math Integrated Math 2 textbook, looking at section 4.3, solving quadratic equations using square roots. Now, so far we've solved quadratic equations by factoring. That went back in, I believe, even chapter 2. And we started graphing equations in chapter 3. We solved quadratic equations by graphing, in section 4.2. And honestly, I think this is more of a follow-up to 4.1, where we did use simplified radicals, where we literally simplified square roots and we rationalized the denominator. 2 bits of 4.1 where I'm not going to reteach. I'm sure even the book won't reteach. They'll say, hey, simplify and you're good. You're golden. So if you have not yet seen 4.1 in my video series, or you don't know how to simplify radicals, I suggest you find the means to do so. 4.1 can be found in my playlist in the description section down below, where we simplify radicals. So again, if you're not too lost on that, I imagine we're going to be doing a whole bunch of that. I also think that that'll help speed up this video more. I mean, you already know how long this thing is by the time slider, but I think that this will obviously be significantly faster because it's based off some of the previous stuff we know. It's not a lot of new stuff involved here, per se. I can find different ways of explaining how things are. I'm sure they will as well, which has to do with solving by factoring a little bit. And there are less problems here. I think there are less than 50, something in the 40s for the problem set. So I'm kind of excited about that. We might use some graphing here and there to realize something. I got my calculator up just in case, all that stuff. Let's go ahead and get started and look at the lecture portion of what they want us to see here for section 4.3. Let's begin with saying we're going to solve quadratic equations using square roots. And all the other ones, 4.4 and 4.5 as well, are going to have square roots involved in some way, so just be ready for that. And approximate the solutions of quadratic equations, which does indeed sound like we are going to be using our calculator here. So previous core vocabulary is square root and the zero of a function. The square root is, of course, just using the symbol involved right there. And then zero of a function being when you set y equal to 0 to solve for x. Okay, early in the chapter you studied properties of square roots. Now you'll use square roots to solve quadratic equations of the form ax squared plus c equals 0. If you notice, there is no bx term. There is no linear term. So we can actually isolate x squared. We can get this by itself, not have an x term in the way, and there's a easier way to go ahead and solve that, even if it's unfactorable, because we've done it by factoring. But now if it's unfactorable, or if you want to find it by any means, we can do that. We solve by taking the square root of each side. So here's what it's going to look like. If x squared equals d, and I'm reading this on the fly with you guys, but if x squared equals d and d is a positive number, see, d is going to be a number. If d is a positive number, x squared is going to have two real solutions. And they're missing something here. This should say plus or minus the square root of d. And you're going to see why that is through other problems. I'll talk about it. Maybe through the examples. Perfect. They're going to show it right here. When d equals 0, x squared equals d will only have one real solution, and it will be 0. If you take the square root of 0, you get 0 out. And when d is less than 0, then x squared equals d has no real solutions, because you can't take the square root of a negative number and get a real number back out. If we graphed that, we would see that your graph would not cross it would not have x-intercepts. It would not cross the x-axis. So the first example they have, solving quadratic equations using square roots, we have to get the x squared by itself, and it takes 2 steps. First, we would add 27 to both sides, and then we would divide both sides by 3. You're now at the stage x squared equals 9. From here, you take the square root of both sides, and then you get here x squared equals plus or minus the square root of 9, which means plus or minus 3. Keep in mind, those are two different solutions. This is just a condensed way of saying it in one equal sign here, 3 and negative 3. Now the plus or minus is the part that's most often forgotten by students, and you might be wondering why we're including it. Well, let's look at it in two formats. The first one, and I don't think they're going back and double checking, so let's go and double check. We're asking what values of x would make this statement true, the original statement that we have. And the fact of the matter is 3 clearly works. 3 squared is 9 times 3 is 27 minus 27 is 0. But negative 3 can also work. You see, when we square a number, it turns positive, or the result of squaring a number is positive, and we don't know whether that number was positive or negative to begin with. We need to account for the fact that this value may have been negative. Negative 3 squared is also 9, positive 9. times 3 is 27, minus 27 is 0. So both of these solutions are valid. They both do work. Another form of looking at this, of course, is solving this by factoring, which we have done in the past, and this is what they're showing you. If you factor 3 out, you now construct a difference of two squares, x squared minus 9, which factors to x minus 3 times x plus 3. And the two solutions for that are 3 and negative 3. So you get the same number of solutions that way. A third way of seeing it, of course, is through the graph. If I graphed y equals 3x squared minus 27, I'm not going to get deep into the notion, but it's a parabola. It would go like this, and it would cross at the x-intercepts of negative 3 and positive 3. So there's no denying the fact that the negative part is a solution to this. We just got to recognize kind of where it comes from. Now, there is an in-between step that they're not showing. This is assuming x can represent any real number, positive or negative, that the square root of x squared doesn't just cancel out the x's for that reason. It's actually also called the absolute value of x. And we haven't talked about absolute values in this book. It's something you would have done in the Integrated Math 1 section of Big Ideas Math, as if to say that if the absolute value of x equals 3, then the absolute value, the two numbers you can take the absolute value to get 3 are 3 or negative 3. So they both would have easily applied as well. And this is also a true statement within, which I will never be writing. The book might at some points, and we can kind of skip that, but you do have to remember the plus or minus. And I know I'm spending a long time talking about that, but I want to remind you of that. So there are two solutions. Two solutions. Okay. Second one, x squared minus 10 equals negative 10. If I add 10 to both sides, I do get 0 out on the right side, and the square root of 0, take the square root of both sides, does just give you 0. You could say plus or minus 0, but 0 is neither positive nor negative. It is neutral. There is only one solution, which also means in terms of that graphing set, your vertex is on the x-axis. Solve negative 5x squared plus 11 equals 16. If you subtract 11 from both sides and divide both sides by negative 5, you get x squared equals negative 1. If you take the square root of both sides like that, you can't get the square root of negative 1 isn't negative 1, because negative 1 squared isn't negative 1, it's positive 1. There's no real solution to this. There is just another set of kind of solutions we talk about in the future. I think around 4.6, 4.7, which are imaginary solutions, but not here. Just saying no real solutions for now. But just as a teaser, you will be seeing some later. Okay, now before we were talking about getting x squared by itself. Now in the case of having something factored here, like x minus 1 quantity squared, it's just all about isolating the squared quantity, the quantity that does have x in it, because I can take the square root of a quantity that is squared and do the same thing. If I take the square root of both sides here, I'll get the quantity that's canceling here. To get x minus 1 is plus or minus 5, and it's weird they don't have the plus or minuses in my digital file. I assume the one I attached online on YouTube here also won't have it. If you add 1 to both sides, notice they put the 1 in front, but it's 1 plus or minus 5. And there you want to actually present what those two solutions actually are. Like 1 plus 5 gives you 6, and 1 minus 5 gets you negative 4. So the two solutions are 6 and negative 4. And you do want to put the 1 in front. There's a visual aesthetic to that we're going to see when we solve in 4.5, in section 4.5. You just want to stick that 1 out in front. Just get used to that. But the plus or minus only applies to adding or subtracting 5, that other number there. They do show using a graphing calculator to check these things. If you graph the original equation where it was x squared, x minus 1 quantity squared minus 25, or y equals that, and you get the solutions crossing at negative 4 and positive 6. So they are showing that representation now. Skipping some of those steps because we're going to do them in the problem set. Now we'll talk about approximating solutions. Now, if they ask us to round to the nearest hundredth, we will do so. But if I'm always going to simplify a radical beforehand if I'm able to. So, on the previous problems that you all just saw, guys, by the way, we could have solved using some form of, difference of two squares, some stuff like that. And there's this other version is going to be using something out of section 4.4 called completing the square. But if it's not factorable, if there aren't integer or rational solutions, solving using square roots is appropriate for a situation where there's only a quadratic term, no linear term, and some constant term. In this situation, when you add 13 to both sides and divide both sides by 4, you get x squared equals 7. We'll take the square root of both sides here. The square root of 7 is not a perfect square, so we can leave it as the square root of 7, or in this case, plus or minus the square root of 7. And then they use the calculator to approximate that. That's plus or minus about 2.65. This is approximated. It's not exact. This is exact. So this is a great answer if they say solve. If they say solve by rounding, that's that. So positive 2.65, negative 2.65. You can see on the calculator oh, over here, where they are crossing against that line when it's set equal to 15, I guess it looks like. Okay, so that's one set of those. And then, yeah, we're going to do a lot more approximations. Give me 1 second. Okay. Solving a real-life problem. A touch tank has a height of 3 feet. Its length is 3 times its width. So we'll set up a scenario with that. The volume of the tank is 270 cubic feet. Find the length and width of the tank. If you have a width that's W, the length can be expressed as 3W, so we can have one variable in this scenario. We know that the height is a constant of 3. So we substitute 3 for H. W will remain W, as length is 3 W's together. Length times width times height gives you the volume of this rectangular prism scenario, as it is a touch tank, and set equal to 270. So that multiplies to 9W squared. If I divide both sides by 9, I can get my W squared by itself. And we take the square root of W squared and the square root of 30, and then we get this. Now, as far as simplifying radicals, this doesn't have any perfect square factors, so I would leave it. So W is plus or minus root 30. However, negative root 30 should not be able to apply for our scenario because they say use positive solution because we can have negative width. So they say what? Find what? The length and width. So we already know the height is 3. The width is root 30, so the length is 3 times that amount, which is around 16.4 feet. And notice this, guys, just so you know, by the way. Notice how they say this is about 5.5 feet, and this is about 16.4 feet. Well, if I tripled 5.5, I would get 16.5. So how come they got 16.4? Because 5.5 is some rounded version of the square root of 30. You don't want to use the rounded version and triple it. You want to use the exact value and triple it. So this number rounded is closer to 5.5, whereas this number rounded is closer to 16.4. I don't want to just triple 5.5 and say that's going to be the answer. You don't want to round early. Rearranging and evaluating a formula, we have the area of an equilateral triangle with side length S given by this formula here. I'm sure I could have spent some time to come up with that myself. Got a yield sign where all these lengths are S. We're going to solve the formula for S, then approximate the side length of the traffic sign that has an area of 390 square inches. So they basically want you to get S by itself in this equation. Now, we're going to first multiply by the reciprocal, 4 over root 3 on both sides. Looks like they wrote that here, times 4 over root 3 to then cancel those guys out. S squared is by itself, and then you take the square root of both sides, and you get this crazy look of square root of 4a over square root of 3. We normally wouldn't want something to have a square root within a square root. Even the square root of 4 could have turned into 2. A lot of different things could have made things look a little bit better, but we're just going to plug something in and see what happens. When you substitute 390 into there, it looks like they get about 30 inches for the length of any side. Remember, they gave us the area amount, and they said find what each side length would be for that area for that equilateral triangle. It's about 30 inches. Okay, that's it for the lecture portion. Let's take a look at the vocabulary and core concept check numbers 1 and 2. Then we'll do the full problem set here. Get everything ready. Complete the sentence. The equation x squared equals d has blank real solutions when d is greater than 0. If you have a positive number here, you take the square root of both sides. You're going to have 2 real solutions. This is going to be a positive and negative version of a number that we can square to get that positive value out. All right, number 2, different words, same question. Which is different? Find both answers. If solving this using square roots here is A, solving this using square roots should be the same thing because I can add 144 to both sides there. That's the same. If I subtract 146 to both sides, this would say x squared equals negative 144. That looks different. And for now, I'm going to put B. That would have no real solutions. If I subtract 2 from both sides, yeah, that would say x squared equals 144, as this would equal 144 as well. This would be A. So this guy is different. This would have the no real solutions, and this would have plus or minus 12, because I can take the square root of both sides and get a 12 out, positive or negative 12 there. So those are the 2. All right, guys, we're going to go and move forward and see how the rest looks here. Hopefully this will start to make sense. They mentioned nothing so far about simplifying radicals, and they've had no problems present where we needed to simplify radicals, which I hope we get to run in some here. I know they're going to ask us to do some using the calculator to approximate, especially on word problems, but I hope to make use of the radical stuff that we practiced before. So just get ready for that. I sure hope it comes up. Let's see what we got. Okay, we have numbers 3 through 8 where we determine the number of real solutions and then we solve using square roots. So we are going to actually write how many solutions before or after we actually come up with that number. So for x squared equals 25, we will have two real solutions. This is because 25 is a positive number. And by the way, we only state that once we have x squared isolated on one side of the equation. If I take the square root of both sides here, this is where we will get x equals positive or negative 5. Do not forget there are two answers to that set. Right? That's part of it. If you identify how many solutions there are, then maybe that helps remind you of what's going to actually happen. Now, number 4, you see x squared equals negative 36. X squared being, once again, isolated, but 36 being negative, we are going to have no real solutions, which means there's nothing else to solve from here. I mean, for now. Once we hit a later section, we will be finding the imaginary solutions to the set. However, here, no real solutions, and we move forward. Number 5 is the same case, x squared equals negative 21. Once again, x squared isolated and 21 being a negative number, there are once again no real solutions. I will happily copy and paste this thing over and just move forward. Number 6, we have x squared equals 400. 400 being a positive number, we will have real solutions of the amount of 2. X squared equals 400. 2 real solutions, once again. Good old copy and paste job. Why not? Faster for me. You can just pause and move forward, but I will take the square root of both sides to then solve this thing. The square root of x squared is the absolute value of x. Therefore, x would be positive or negative 20. 400 being a perfect square of the number 20. Number 7, x squared equals 0. I mean, I can kind of state, kind of moving forward here, when I take the square root of 0, I will be getting 0 out as the only one real solution. There's only one value I can square to get 0, which is 0. X is no plus or minus 0. No, just 0. Take the square root. X equals 0. And then number 8, x squared equals 169. Also a positive, perfect square. By the way, it doesn't need to be a perfect square to have this many real solutions. But to be rational, it would. 2 real solutions. Should have copied and pasted. Actually, that looks pretty hideous. Let's copy and paste anyway. Boom. All right, take the square root of both sides. And we get x equals plus or minus 13. Because 13 squared is 169. Good, we are well on our way. Let's keep moving forward. On numbers 9 to 18, we will solve the equation using square roots. I will not write how many real solutions there are anymore. Now it's time for us to go with it. And keep in mind, it's not the original problem that determines how many real solutions there are. I see a 0 on this side. Does that mean there's only one real solution? No, you got to get x squared by itself first before you make that determination. If I add 16 to both sides, I'll get x squared equals 16, which means there will be 2 real solutions because that d is positive. If I take the square root of both sides, I will get x equals positive 4 or negative 4. Number 10, x squared minus or plus 6 equals 0. But when I subtract 6 from both sides, you will get x squared equals negative 6. There are no real solutions to this case because you cannot take the square root of a negative number and get real values out. So once again, it's said equal to 0, but once I subtracted that over, then we're at the stage where we can make that determination. It's all about the thing you're taking the square root of, right? Now, I'm not taking the square root early. There's no premature state for which we can or should be doing that with how these look. I got 2 things to do here. I am going to be subtracting 12 from both sides, kind of a warning sign with that being negative, and then I'll divide both sides by 3, and it still appears negative. Once again, no real solutions in a case like this. It doesn't look like I can just copy that one phrase. No real solutions because I have a negative 4 over on that side. Number 12, x squared minus 55 equals 26. Let's add 55 to both sides and we get a larger number, like 81. I get to now take the square root of both sides and we will get x equals plus or minus 9. 2 solutions, positive 9 and negative 9. I'm excited that this video might be able to go pretty fast here. Number 13. 2x squared minus 98 equals 0. 2 steps to go. Let's first get the x squared term by itself by adding 98 to both sides. Then we'll divide both sides by 2 and get 49. When you take the square root of both sides, we will get x is positive or negative 7. Number 14. Well, I like where they're going to begin with on this, with x squared being negative. Remember, x squared is not isolated if it says negative x squared. However, we are subtracting 9 from both sides to get 0, which will lead us to a moot point compared to other cases. If I divide both sides by negative 1, I still have 0 on that side, meaning no signs change. When I take the square root of both sides, though, I still get x equals 0 as my solution, my one and only solution. I wish they saved, I wish they saved negative x squareds for different problems, but they just did it again. So let's take a look at number 15. On number 15, we have negative 3x squared minus 5 equals negative 5. If I add 5 to both sides, we will get negative 3x squared equals 0. Divide both sides by negative 3. You still get x squared equals 0. Take the square root of both sides. You still get x equals 0. Once again, I mean, come on. Let's give us a problem where we divide by a negative to change signs, not to keep it as 0. I'd very much appreciate that. Doesn't look like that's showing up for these other next few problems, though. Number 16. 4x squared minus 371 equals 29. 4x squared equals 400 if I go ahead and add 371 on both sides. By the way, I could take the square root of both sides here. I don't encourage it. I really don't. There are things where people are just not aware of the fact that this would have to be square rooted as well. You can't do it when there's a sum involved. Just divide by the thing first. Divide both sides by 4. We are going to get 100. Nothing lost, forgotten, as long as this could combine through division. If I take the square root of both sides now, we will get positive or negative 10, plus or minus 10. Number 17. Oh, good. At least we have this example here. Yeah, this is one of the times where it actually might be forgotten. But 4x squared plus 10 equals 11. We will subtract 10 from both sides and get 4x squared equals 1. Divide both sides by 4, we get x squared equals 1/4. Okay, now this is time to use a property of radicals that we got to use in the past, both in Chapter 1 and in Section 4.1. When you take the square root here, we are taking the square root of the top and the bottom, and this is still a plus or minus that's going to happen. The square root of 1 is 1, the square root of 4 is 2. It's not simplifying the radical per se, but we did get to use a top and bottom portion. We can't leave it like this, and yes, both get, plus or minus. Yes, both get added and subtracted. Square rooted. And then number 18, 9x squared minus 35 equals 14. Let's add 35 to both sides and get 9x squared equals 49. Divide both sides by 9 and we get x squared equals 49 over 9. Now this cannot reduce as a fraction. They don't have anything in common. However, we will be taking the square root of both sides and getting ourselves a plus or minus here. We get to take square root of 49, which is 7, square root of 9, which is not 9, which is 3, and we will get positive or plus or minus 7 thirds. They're not asking us to round, and I wouldn't expect it. This is a nice exact answer, or two answers I should say, and we are good to go. All right, that is numbers 9 through 18. Let's keep proceeding forward. Let's look at numbers 19 to 24, solving using square roots. This is a problem set where x plus 3 squared equals 0. We just want the quantity that is squared to be isolated, and we are very much in that form right now. So it is from here that we would love to take the square root of both sides. This is where you are just left with x plus 3 as a whole, and that equals 0. There's no plus or minus involved. That subtract 3 from both sides, we get x equals negative 3. Number 20. X minus 1 quantity squared equals 4. The quadratic, the squared quantity is isolated. We will take the square root of both sides from here. It's where we get x minus 1 equals. And we have positive or negative 2. Square root of 4 is 2. I can add 1 to both sides, and we will get 1 plus or minus 2. You do not leave your answer like this as long as things can combine. In other words, we can do x is 1 plus 2, and x is 1 minus 2. It's just a positive 1 that adds 2 and subtracts 2, where we get 3 or negative 1. It's not the opposite. It's not plus or minus 3 or something like that. From 1 we add or subtract 2, and that's what we get. Number 21. 2x minus 1 quantity squared equals 81. Once more, our squared term is isolated, the squared quantity, I should say. Take the square root of both sides, and we will get 2x minus 1 here. And this is positive or negative 9, plus or minus 9. Now, there's still 2 more steps. We're going to add 1 to both sides and get 1 plus or minus 9, and we divide by 2, and we get 1 plus or minus 9 all over 2. And once again, we kind of want to write out what those 2 solutions are. There's 1 plus 9 over 2, which is 10 over 2, or 5. And there's 1 minus 9 over 2, which is negative 8 over 2, or negative 4. Those are the 2 different possible solutions based off of that split that set up those 2 conditions. Number 22, same kind of problem. 4x plus 5 quantity squared equals 9. Let's take the square root of both sides from this stage here. We do get 4x plus 5 on the left, plus or minus 3 on the right, square root of 9. Let's subtract 5 from both sides, negative 5 plus 3, negative 5 minus 3, and divide both sides by 4 from there. So we have 2 different things to have, negative 5 plus 3 being negative 2, and negative 2 over 4 is negative 1/2. And then negative 5 minus 3 is negative 8. Dividing that by 4, we will get negative 2. So negative 1/2 and negative 2. Number 23. 9 times x plus 1 quantity squared equals 16. Once again, this is a kind of thing where I could take the square root here, but you would have to remember it applies to the entire product. Instead, let's just divide both sides by 9 and stick with our rule of isolating the squared term first. It keeps a lot more things intact. I think people will remember to do it a little more so at this stage when it's here. Now we just have x plus 1 that remains. Square root of 16 is 4. Square root of 9 is 3. So plus or minus 4/3. Here we'll get negative 1 plus or minus 4/3. And yes, there is a time and place where we want to find a common denominator, and this will be among it. So negative 1 is also written as negative 3 over 3. The idea here is you want to get a common denominator. So even joining these up, we can say, actually here before I do that, we can say negative 3 plus or minus 4 all divided by 3. Common denominator means we get to add the top and keep the bottom. And like I said, this thing will look, you want some familiarity in terms of this appearance. It'll be important when 4 is a radical value instead of actually just a square root, a perfect square root thing. So what are our 2 solutions? Negative 3 plus 4 being 1, and 1 divided by 3 is, yes, exactly that. Negative 3 minus 4 is negative 7, and we get negative 7/3 out of that one. Those are your 2 solutions. And then we have number 24. As we wrap up this set, where it asks us to solve 4 times x minus 2 quantity squared equals 25. Let's divide both sides by 4 before we take that square root. We will get 25/4. We cannot simplify or reduce that fraction. Let's take the square root of both sides. We get x minus 2 on the left. Plus or minus, square root of 25 is 5. Square root of 4 is 2 on the right. Let's add that 2 over, and we get 2 plus or minus 5 over 2. Or 2 is also 4 halves. 4 halves plus or minus 5 halves, which is also written as 4 plus or minus 5 all over 2. That's probably a lot to write if you think you can get them all in one step to write it that way, or before you do, after you start doing the split, you can join them, that kind of thing. I'm just once again giving you something just in case we're going to run into problems like that. I kind of hope we do. So we have 4 plus 5, which is 9, or 9 halves. I know that's 4.5, but I think it's best left that we leave them as fractions as long as we can. 4 minus 5 is negative 1, negative 1/2 being the other answer. Okay, that's it for that problem set, and then we move forward to 25 to 30. Looks like we see the first 4 of those. right here, we're going to solve the equation using square roots and round our solutions to the nearest 100th. Excuse me. So we are going to jump on to number 25, where we have x squared plus 6 equals 13. I subtract 6 from both sides, and I get 7. It's kind of like the example that we saw. This is a case where we take the square root of both sides. The official exact answer is plus or minus square root of 7. But we need to take that square root of 7 in our calculator and make sure we write what those two solutions are to 2 decimal places. Okay, that's where we're going to go, 2 decimal places. So let's go to here, and let's check out square root of 7. I forget, it was 2.85 or something. 2.65. So around 2.65, and that's how we say that. X is going to be approximately positive or negative 2.65. If we have to write both answers separately, there's 2.65 and negative 2.65, rounded. Same with the radicals. Number 26, x squared plus 11 equals 24. You know, I find it interesting. I hope it's going to come up in a second, but I find it interesting that we're not running into problems that are akin to 4.1 where we simplified radicals. Actually, no, not this problem. You know, I hope it comes up because the whole point of simplifying was to do it for problems like this. Obviously, there are some problems where we're going to be able to do it. We'll find out when that is. We take the square root of both sides, and we will get x squared equals plus, or excuse me, x equals plus or minus the square root of 13 as an exact answer. An approximated one, just take my word for it. I'm going to do it on the calculator. And I'm getting 3.60555. So about 3.61. 3.61. Rounded. Number 27. Oh, I think they're finally showing... Oh, wait. Not on this problem. Sorry. I got it. Well? No. 2x squared minus 9... no. 2x squared minus 9 equals 11. We're going to add 9 to both sides. 2x squared equals 20. I inject my opinion, maybe a little too much. And divide by 2, you get x squared equals 10. So taking the square root of both sides, we'll get x equals plus or minus square root of 10. 10 not being simplifiable. Darn, we missed it. Plus or minus square root of 10 as 2 exact answers, 2 real solutions we can write out of that thing. But let's go and take the square root of 10. It's around 3.1, I think. Let's see. 3.16. So closer to 3.2, actually. Plus or minus 3.16227766. Number 28, signs of life. Number 28 actually gives us something out of what 4.1 would have asked us to do when it comes to an exact answer. I'm actually looking forward to it. 5x squared plus 2 equals 6. I won't teach it again. I'm just going to do it. Subtract 2 from both sides, and you get 4. Divide both sides by 5, and you get 4/5. Take the square root of both sides. Here's where this comes up. And we get x is plus or minus, the square root of 4 is 2, and the square root of 5 can't be simplified, so we write it like that. However, we have an irrational denominator. Yes, I get to rationalize the denominator, multiply top and bottom by square root of 5. And I know the book's just asking you to round. We'll get there. They do say solve using square roots, and then they say round. So we're going to do that. So it's plus or minus 2 root 5, all divided by 5. At the very least, I got that portion of something to write that's exact. Now, I'm just going to use 2 divided by root 5 on my calculator because that's faster to type out. So it should be the same answer, right? That's the whole point of simplifying. 0.89 about, 4 and all that stuff. So plus or minus 0.89. And it should be less than 1. 4/5 was less than 1, and you take the square root of that, basically. I mean, exactly. You are taking... Actually, that would have been faster, taking the square root of 4/5. All right. Numbers 29 and 30 still left to go on this set. Maybe some more of that rationalizing coming in. We have negative 21 equals 15 minus 2x squared. I'll keep the 2x squared negative. I just want to make a point of what I'm going to do here. Subtract 15 to both sides, and you get negative 36. And then when I divide by negative 2, what was negative here will turn positive. So we will get positive 18. And we can actually simplify this guy. You take the square root of this. I'm going to put x on this side. It's plus or minus. Square root of 18 is root 9 times root 2. The square root of 9 is 3. we get 3 root 2. Again, that's something out of section 4.1. Cool, they are throwing some in the way for us. I am very excited. So square root of 18 is what I'm going to type in the calculator. And I get 4.24 about. So plus or minus, that is not a plus. Plus or minus 4.24. So exact, approximated. You can bet I care more about the exact unless we're dealing with graphing it or word problems. Number 30. 2 equals 4x squared minus 5. You can tell we're not as interested in real solutions or no real solutions anymore. Add 5 to both sides. Divide both sides by 4, and you're going to get 7/4. Taking the square root, not as fun here. Nothing to rationalize or simplify in full. But we do get to take the square root on the top and bottom. Square root of 7 is exactly that. Square root of 4 is 2. So let's go ahead and compute what that's going to look like. 1.32, about plus or minus 1.32. Okay, exact, approximated, all good. All right. I think we're about 2/3 of the way done, which is pretty cool. Pretty cool. It's the shortest section yet so far. Number 31, error analysis. Describe and correct the error in solving this equation. So let's take a look at what they did. Looks like they added 33 to both sides incorrectly, divided both sides by 2 correctly, took the square root correct-ish. However, there should be 2 solutions. There should be a positive and a negative 6. Because squaring a negative, that's how I'm going to explain it, squaring a negative should have also led to a positive result, all that stuff. They obtained one correct solution, but never determined the negative solution to the equation. I don't know how I want to explain this. So let's just describe and correct the error, but squaring would okay, so 2 solutions. So correcting the bit, I'm just going to start from where it said x squared equals. So if x squared equals 36, we take the square root of both sides, we'll get x equals plus or minus 6. Okay, they were pretty close. But that's exactly where most students would falter as well, which is why it's always a good problem to have. Number 32. An in-ground pond has the shape of a rectangular prism. Really? It looks kind of elliptical. The pond has a depth of 24 inches and a volume of 7,200 cubic inches. The length of the pond is 2 times its width. Find the length and width of the pond. All right, depth is also height for me, so I'm just going to say for this, volume is length times width times height for this rectangular prism. The height is going to be that 24 inches, and the width is going to be W, and the length is twice that of the width. So you take twice that of the width, you get the length. So for us, the volume also, by the way, was 72. I said 7,200. I meant 72,000. 72,000 cubic inches. So we are going to be doing 72,000. I'll write that on the right. Equals the length times the width times the height. 2 times 24 is 48. W times W is W squared. You get this here. That is supposed to be 7. 72,000. Let's divide both sides by 48, and you get W squared equals, 48. It's like 150? Or 1,500? Let's see. Sorry, let me... 1,500. So W squared is 1,500. Now, as for me, I'm personally curious about the exact answer here first, as far as the whole plus or minus thing. 1,500, it definitely has 100 in it. Yeah, 100 with 15 will totally work. So square root of 100 times square root of 15, or plus or minus 10 root 15 inches. Now, we are going to ignore the negative answer, And we are, of course, going to be rounding this thing. However, I will need to use my exact answer to find the other thing as well. So I am glad that I do have this. I'm going to go ahead and get rid of the negative portion. Let's cross it out from back here, and let's go and erase it from here. So it's exactly 10 root 15 inches, but which is approximately, this is where I get around to the nearest hundredth for myself. So square root of 1500, or 10 root 15, 38.73 inches. However, I will not be using the rounded version to calculate the length. I will be doubling this. So the length is double 10 root 15, which is 20 root 15. And that's about 77.46, which actually does end up being the same rounded as the one if I doubled, but it didn't have to be. Didn't have to be, so you just have to keep that in mind. So that is the length, that is the width, and the height or the depth was 24 inches. Okay, now that we're hitting word problems, you can see it slows up a little bit, so we'll see where we go from here. Modeling with mathematics, number 33. A person sitting in the top row of the bleachers at a sporting event drops a pair of sunglasses from a height of 24 feet. The function h of x equals negative 16x squared plus 24 represents the height and feet of the sunglasses after x seconds. How long does it take the sunglasses to hit the ground? So, all right, so here's where I'm kind of like glad and all that. In the past, we would have problems where I'd have to graph this. And I'd say there are other means to solve it algebraically, including difference of two squares factoring. But we were in graphing stuff. But now we're straight in solving using square roots, so I feel very comfortable in saying we can do this. I'm setting the height equal to 0 in this model, and I want to solve for x. X being the number of seconds that pass by, h being the height. The 24 feet have already been applied to the model, where they are in the bleachers, and 0 is the height of the ground. We want to find for what value of x do we get a height of 0. So we're going to solve. I'm going to add 16x squared to both sides. I think it's more feasible to do it that way. And let's divide both sides by 16. And we're going to get x squared equals 24 over 16, which reduces to 3 over 2. Now, we are, of course, going to be taking the square root of both sides, and we will be approximating an answer. But before that, leading up to it, let's have some fun. We get the square... listen, there's a plus or minus. I'm going to ignore the negative when it comes to time. So just root 3 over root 2. And I'm going to rationalize the denominator by multiplying both sides by root 2 to get square root of 6 all over 2. This is in seconds. And of course, this is not how we evaluate things, so I am going to be approximating this. So we're getting about 1.22 seconds. That almost seems like a long time, but I believe it. I trust it. All right, that is number 33. Give me one moment. Okay. Number 34. Your friend says the solution of the equation x squared plus 4 equals 0 is x equals 0. Your cousin, I never had a cousin in this scenario. Your cousin says the equation has no real solutions. Who is correct? Explain your reasoning. Excuse me. All right, so x squared plus 4 equals 0. Your cousin's correct, but in order to explain it, I'd also like to go into explaining it says, hey, let's just solve it, I suppose. But let's go into the reason why your friend might have said that to begin with. So I can think of other answers that some people would be putting other than this. I wish that they put, because how people really think on this. Your cousin is correct. Your friend likely saw the 0 and simply assumed that when taking the square root, you arrive at the answer. However, you must subtract 4 from both sides first before solving, and taking the square root of a negative does not yield any solutions. This is why your cousin's correct. Now, let me give you a heads up on a problem like this. This is where you got to be careful. This is where, I'm not saying my students, I'm saying you guys too. Anyone who's watching this, my students, any other students included, this is where people make mistakes. Taking the square root of both sides right now. And I'm not saying with the way the friend did it. I'm saying doing this. Calling this x plus 2. Oh, no, 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 honey. No, this is not how you do it. X equals negative 2. No. 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 You cannot take the square root of a sum and separate into two square roots. The square root of a plus b does not equal the square root of a plus the square root of b. Math just does not operate in that format. You don't do that at all. This is where, this is what I wish they had in the problem. I don't think they know how students think in these terms, but they absolutely do. I know where they're getting at with that zero portion. I get that. That's fine. I'm talking about this, though. That guy here. No. No. Let me put this in red as well. Okay? I gotta make that big stink. I'm letting all you guys know about that right now. Don't start doing that. Isolate your quadratic term or quantity before you take any square roots. Okay? And by the way, that thing works for products. It works for quotients. It does not work for sums or differences. I give many reasons to explain why that doesn't work. And remember, it doesn't work the other way, too, when we square something, right? A plus b squared doesn't equal a squared plus b squared. That's not what squaring something means. That's not just how it comes out to be. So, just something to be very, very careful of. Okay, the design of a square rug for your living room is shown. You want the area of the inner square to be 25% of the total area of the rug. Find the side length of the inner square. So, we have, let's see. They want the area of the inner square to be the, okay. So we have a rug. I'm going to copy and paste this guy here. We have a rug with an inner and outer square. And there's that X on the inside representing the inner square. So how do they say it? They want it to be 25% of the total area of the rug. So the area of the rug is going to be 6 squared, which is 36 square feet. We want 4 of these x squareds to equal, right? That's 25%, which is a quarter of something, right? So we want 4 of these x squareds to equal the area of the rug, basically. That's our setup. Whether you want to say it like this, or taking 25% is where, where you divide things by 4 here. I was just thinking in terms of how I can get a setup and then divide. So x squared is 9. You take the square root of both sides, we're going to get 3. Remember, there's no negative 3 for the sake of the word problem. But the side length x of the inner square would be 3 feet. Now, that might sound wrong to you, where you're saying, wait, Mr. Robinson, that's only half of that. They said they wanted it to be 25%. Shouldn't it be 1.5? Shouldn't you divide 6 by 4? Yeah, but no. They wanted the area of this thing. Here's where this would be helpful for me to draw. They wanted the area to be 25% of this whole thing here. So take a look at this. And I don't know if they drew this to scale, but what it means is area is 2-dimensional. So they want 4 of these. Check this out. 1. I'm going to copy and paste this. 1, 2. It is kind of to scale. 3. And 4. It takes 4 of these to fill up the area of 1 of these. So you need half the length of a side to do that. It's because there are 2 dimensions to account for, not just 1. So that's kind of what makes that happen the way that it does, where those would be 3 feet each. I hope that kind of makes sense. All right, number 36. And I like that they drew it to scale. That was nice. The area A of a circle with radius r is given by the formula A equals pi r squared. Solve the formula for r. So for A equals pi r squared, let's get r by itself. I will divide both sides by pi to get r squared equals A over pi, and then take the square root of both sides. We will get r equals, remember, radius also has to be positive only, so there's no plus or minus here, just A over pi. It seems like as far as what they did in problems, there's no reason for us to write the rationalized version of that. Sorry, I should put part A right there. No reason for us to write the rationalized version, especially if we're just going to substitute something into there and make it happen. We don't want this root pi over pi nonsense. B, use the formula from part A to find the radius of each circle. So now finding the radius by substituting something in for A. So for B, we'll get, for the first circle, R1, we'll get the square root of 113 over pi. I guess that's exact, but I'm going to go ahead and round that thing. Square root of 113 divided by pi. Oh, I didn't hit the division sign. Divided by pi. And I have 5.997, so around 6 feet. Second radius is square root of 1810 over pi. This is in inches, by the way. So let's check that out. Maybe these are all near whole numbers, so maybe I don't have to round these like this over pi. Yeah, 24.00. So I'm just going to put 6 feet. So 6 feet here. This next one is 24 inches. So 24 inches. It's very approximate. It's 0.0029351. And then the third one's radius. Let's see if this stays similar-esque. 531 over pi. Because it's likely they found a number for the radius, whatever, to use, and then they put these in. So 531 divided by pi. Okay, which is 13, yeah, 13.000. So about 13 meters for this last one there. Part C, explain why it is beneficial to solve the formula for R before finding the radius. Because it's a simple plugin. At this point, we have everything taken care of. See, imagine that you had area here. We put 113 into here. Then you have to say, now we divide both sides by pi. Now we take the square root of both sides. It takes more steps to get that. I know that's what we're writing in our calculation, but we have everything involved that we need to calculate now. It is beneficial to solve the formula for R before finding the radius, because we don't need to redundantly use extra solving steps before calculating each and every time. We're basically at that stage now. I mean, we're going to, in 4.5, solve using what's called the quadratic formula. Imagine that every time you were already in standard form, you don't know anything that I'm talking about right now, you don't understand it, but imagine always being in standard form and needing to solve that each time. I guess that's called completing the square, so it's possible. But you're going to be thankful to have the quadratic formula, but that's why we sometimes get things by itself that way early on. Okay, number 37. How can you approximate the roots of a quadratic equation when the roots are not integers? Use a calculator. I don't know if they mean without a calculator. I don't know if they mean, yeah, there's a way of approximating square roots in general. It's like using a slope kind of thing. I don't know what they mean. I'm just going to use a calculator. I'm actually not sure what they're getting at. I don't know what they're getting at. Sorry about that. Number 38. Given the equation ax squared plus c equals 0, describe the values of a and c so the equation has the following number of solutions. 2 real solutions, 1 real solution, no real solutions. Okay. For 2 real solutions, if I subtract c over, that would make c negative. Well, that's if c is positive. So if c is greater than 0, if c was a positive number, y'all, and I subtracted that positive number over, it would be turning negative, which means the only way to get 2 real solutions is a would have to be negative as well. So if c is greater than 0, then a would have to be greater than 0. If c was a negative number to begin with, then a would also have to be negative, because I'm sorry, if c was greater than 0, a would have to be less than 0. A would have to be a negative number in this case. If c was less than 0 and negative, then I'd be adding it over. Then a would have to be a positive number to counter that and make that happen. So those are the two ways that I think we can talk about that for two real solutions. One real solution, the one real solution case is when you're taking the square root of 0, which means you're not adding or subtracting anything in this case here. That would mean that c would have to equal 0. I don't even think that we need the if here. I'm just kind of coming up with these scenarios. If c is 0, now a is not allowed to be 0. For one, you need a quadratic in general. A can be whatever it wants to be, as long as it's not 0. But it can never be 0 in any case, so we're good. Just there. C is going to equal 0, A is not. 0 real solution sounds like it would be the opposite of the 2 real solutions case. If C is greater than 0, A would have to be greater than 0 because that would keep it negative. And if C was less than 0, A would have to be less than 0. I think I could write that a little better, meaning take out the if and put the A's first and the C's second. But I'm getting into the what I have to do with C to make that happen. So that's just how I thought about it in my head. So I wrote it out to make sense of it for you guys. And I think that works for me. All right, number 39. How far are we? Let's see if we can beat the hour mark. I doubt it. Without graphing, where do the graphs of y equals x squared and y equals 9 exist? Explain. Y equals x squared, y equals 9. We want to find out what value of x gives us the same y. So we want to set x squared equal to 9. And then we solve. We take the square root of both sides. We get plus or minus 3. So my explanation is exactly what I just stated. The graphs intersect at some x value or values that result in the same y values. Therefore, if we set both expressions equal to each other, we can solve algebraically. In this case, using square roots. So, where do they intersect? I'm sorry, those aren't just the answers. Those are the x values. Now we substitute 3 and negative 3 into these things, but here's the thing. They're going to intersect at this common 9, right? 3 squared is 9, negative 3 squared is 9. For what x value do we get a y value of 9? That's what we're asking. So 3 comma 9 and negative 3 comma 9. Now this is opposite of what we were doing on section 4.2 solving by graphing. We would take an equation like this and graph y equals x squared and y equals 9 and find where they intersect. So it is the opposite of what that would be, at least in that setup. Number 40. The graph represents the function f of x equals x minus 1 quantity squared. I agree. This is for hk. H is 1, k is 0. How many solutions does the equation x squared minus 1 equals 0 have? Explain. Well, this is more of a solving by graphing scenario. Obviously, we could take the square root of both sides and kind of show that algebraically. So let's go ahead and do that. I'm sorry, I totally wrote that incorrectly. X minus 1 quantity squared equals 0. If I take the square root of both sides, I will get x minus 1 equals 0. There's no plus or minus. We haven't done the plus or minus thing in a long time. And we solve, we get x equals 1. There's one real solution. As far as what they're doing, it's more of like I said, a 4.2 thing. There is one real solution, as we can see by solving algebraically, or by seeing where the graph crosses the x-axis at its vertex, which it only does once. At its vertex. So there's that. It's just right where this thing crosses, because that's where equals 0. This is the y equals 0 part. So it's just the one solution. Okay, number 41. I think this goes up to 44. So number 41. Solve x squared equals 1.44 without using a calculator. Explain your reasoning. Okay, I can see 1.44 as 144, as 144 divided by 100. That's the decimal equivalent written as a fraction. And without reducing anything, guys, if I just took the square roots right now, that would also be pretty ideal, because these are both perfect squares. The square root, and this is a plus or minus, the square root of 144 is whoops, 12, and the square root of 100 is 10, so that's plus or minus 6 over 5. Now it looks like I could have reduced it and gotten to 36 over 25, but that would have taken a moment. So there are those values. Now if you wanted to write the decimal, it's 1.2. So listen, 12 squared is 144, 1.2 squared is 1.44, or you can get those versions of the answers as well, but it is plus or minus. I'm not going to explain my reasoning, I just converted it to a fraction and justifying it through that. Ooh, this looks a little bit like section 4.5, but anyway. The quadratic equation ax squared plus bx plus c equals 0 can be rewritten in the following form. X plus b over 2a squared equals b squared minus 4ac all over 4a squared. Use this form. Now, you don't have to understand that part right now. You will understand this part by section 4.5. But use this form to write the solutions of the equation. They're giving you a little preview of section 4.5. And I know that this looks a little overwhelming. But let's just do what we know how to do. Take the square root of both sides. And we now have x plus b over 2a equals plus or minus. And let's split this up. The square root of b squared, excuse me, this has 4a squared over here. I jumped the gun. B squared minus 4ac here. And down below, we take the square root of 4a squared. The square root of 4 is 2. The square root of a squared is a. Now we subtract b over 2a from both sides, and we'll get negative b over 2a plus or minus the square root of b squared minus 4ac all over 2a. And because we have a common denominator, we can rewrite it as negative b plus or minus the square root of b squared minus 4ac all over 2a. No, this equation means nothing at all, man. Just totally ignore this. This equation means nothing in your life whatsoever. You're not going to see this in a couple sections from now. No, totally not. Totally not. Nope. Just rid it from memory. It's not there. Look, we're past the hour mark, man. We got to keep going. Who needs formulas like this? Number 43. An equation of the graph shown is y equals 1/2 times x minus 1 quantity squared plus 1. Of course it is, because 2, 1's the vertex. Looks like a stretch factor of 1/2 over 1, or compression, over 1 up a half over 2 up 2. Totally, it does. This time I'm not being sarcastic. 2 points on the parabola have y coordinates of 9. Find the x coordinates of those points. They're going to be 6 and negative 2, because you go over 4 and up half of 16. But let's find them by setting 1/2 x minus 2 quantity squared plus 1 equal to 9. Let's subtract 1 from both sides. Let's multiply both sides by 2 times 2 times 2. We'll get x minus 2 quantity squared equals 16. So notice, I didn't expand this thing out, right? I can solve using square roots because I can get this guy by itself. So let's take the square root of both sides to get x minus 2 equals plus or minus 4. And let's add 2 to both sides. I'm having so much trouble writing as I talk. We get x equals 2 plus or minus 4. 2 plus 4 is 6. 2 minus 4 is negative 2. And that's what I stated, 6 and negative 2. Those are both 4 away from 2 and 8 up from 1. 8 being half of 16. And half being our vertical compression factor. Last question, number 44. Solve each equation without graphing. Okay, so I didn't write 44 yet. Let's solve x squared minus 12x plus 36 equals 64. Now, you could probably also solve this by subtracting 64 over and setting it equal to 0. That is not their intent of this problem. For solving, their intent is to solve using square roots. You would have to notice this is a perfect square trinomial of x minus 6 quantity squared. And in doing so, we could take the square root of both sides. You know what would have been better for their case? To have used a number over here that wasn't a perfect square. Anyway. So, you take the square root of both sides, you get x minus 6 equals, and this is positive or negative 8, being the square root of 64. If I add 6 to both sides, I get x equals 6 plus or minus 8. Now, 6 plus 8 is 14. 6 minus 8 is negative 2. It also means this was factorable if I subtracted the 64 over, and I could do some zero product property stuff. But of course, being a perfect square trinomial, that's also what you can do solving using square roots. This leads well into section 4.4, just so you know, on completing the square. Let's solve x squared plus 14x plus 49 equals 16. And once again, they would have made a better case by making this non-factorable if I subtract that over. Making this a non-perfect square, I should say. But this is a perfect square trinomial that factors down into x plus 7 quantity squared. If you take the square root of both sides in this stage, you will get x plus 7 equals plus or minus 4. Subtracting 7 from both sides, you get negative 7 plus or minus 4. Negative 7 plus 4 is negative 3, and negative 7 minus 4 is negative 11. All right, those are the two answers there, and that ought to do it for this one, guys. The only problem where I was kind of like, was this number 37. Sorry about that. I'm sure there's something that I could have written out that was much better. Anyway, that'll do it for this one. This is Mr. Robinson. Thank you so much for watching, and I will see you in the next one. Take care.